polar forms. And after that, we have one more topic. We will talk about this on Thursday. So you have to study until the 15.5, okay, for midterm. Next Monday, you will have midterm. And I think Thursday is December 31. We will see. If it's not public holiday, we will have some short class. We will discuss about the midterm. Otherwise, we will see. Okay, guys, then let's start. We have enough students now. Actually, I was not expected for every student. Now we talk enough. I think we can start class now. So double integrals and polar form. Last time we talked about area by double integration and double integrals over general regions and also over rectangles. But now we will talk about double integrals in polar form. Okay. So again, the idea, the first question comes, okay, why are we learning this? Because you know that sometimes we have a problem. For example, let's say very simple problem is quadratic equation, right? So in different forms, we can solve this, right? For example, the first method is by factorization. Even before factorization, we can try guess and trial method, right? If we just sometimes you can just see the question, for example, x squared is equal to 9, right? Guess and trial method works for this. That's the fastest method. And the second one is factorization method, right? If we cannot guess or our guess does not work that quick, then we need to factorize and solve this. That is also a fast way, but it's a bit slower than the previous one. And how about if factorization doesn't work? Then we can use the formula to solve the quadratic equation. And now, after actually mathematicians like Descartes, for example, in 17th century, they introduced coordinate system. Now people got interested in this new field, coordinate system. That means that what is a coordinate system? It shows, I mean, the importance of coordinate system is there's a kind of interplay or a relation between algebra and geometry, right? So that means that we have an equation, and also by points, right, in the coordinate system, we can describe this. Like, for example, x squared plus y squared equals 4. We know that that is the equation of a circle. But actually, it's not the equation of the circle, right? X squared plus y squared equals 4. It is itself actually an algebraic equation. But, and also actually in the coordinate system, if you talk about a circle, actually they are representing each other in two different worlds. One is the world of algebra, another one is the world of geometry, right? Or let's say coordinate geometry. So that means there's a kind of relationship. Okay, it's like somehow we are using the same rules in both dimensions. And also here, double integrals. Actually, as you see here, we practice a few examples and we try to solve both problems using, in rectangular coordinate system. But some problems you will see that now it is, we don't say that it's not possible, it is possible, but very complicated. But when I just solve that problem using a little bit different method, we can actually reach the solution very fast. And one of the methods here we are going to suggest here is double integrals in polar form. So integrals are sometimes easier to evaluate if we change to polar coordinates. And especially you will see that if our function involves like x squared plus y squared, for example. Okay, in polar coordinate, how do you describe this? We know that x squared plus y squared is just r squared. That is very important point here. So this section shows how to accomplish the change and how to evaluate integrals over regions whose boundaries are given by polar equations. And also we know that when we say polar equations, right, everything is about this. We are talking about this thing, right? Here we have coordinate system that is x and y. If we just pick any point, let's say P, whose coordinates are x and y. So we are talking about this x and y, right? Now also in different way, actually, we can describe this point. Of course, a lot of different ways you can describe this. The easiest one is when the angle is 90 degrees. Another way is, for example, since this origin is our reference point, right? For example, how about if I just define this point as how far is it away from the origin? And what angle we should actually turn, right, to reach that point. That means that just to this piece of information, this theta and the length of this r, right? And also in this, with two information using theta and r, I can describe any point in a unique way in the coordinate system, right? So here we know that by just using trigonometry. So how do you find the relationship here? We know that r is a distance. So from here, r squared is equal to x squared plus y squared. And how about this theta? We know that the theta, right, this x is described as r times cosine of theta, and y is equal to r times sine of theta. So now then, if you're talking about a function, let's say f of x, y, right? So what is x? X is r times cosine of theta. And how about y? Y is r times sine of theta. So actually, we should just, now we were, our function talking about here, right? We have just take this into another kind of space, not space, actually different world. Actually here, who are the main components here? Here, r and theta, right? Everything actually here works with r and theta. Okay, so now I'm dealing with everything with r and theta. So that's all about this polar form actually. And now, of course, there's a little bit change when we are obtaining the double integral. We will talk about this, and after that we see a few problems. That's it. That much is enough. I think that's actually all about this double integrals and polar coordinates. Okay, now let's start, guys. Here again, suppose that we are given a kind of region. Let's say our region is R, that is bounded by two curves. As you see here in the picture, this blue line, right, and also this another blue line here, and this blue line, what is the equation of this blue line? That is r equals g1 of theta, because this r, also this theta is changing, and also this r is changing, right? Another line here is, what is it, g2, right? The second line here, that is g2 of theta. Okay, and also our angles, the angles are changing from theta equals alpha through theta equals beta, right? So now we are talking about this shaded region. Okay, and that is the region that our function is assuming or taking values from this region. So we are talking about this kind of function. Here we have x, y, z. So that's our function. Z equals x and y. So now here we are talking about the function whose actually variables are, what is it? R and theta. Okay, every point here is described by r and theta. Anyway, so we are going to integrate our function over this region. Okay, now actually you're just I would say go through the similar steps. Number one is we have to partition this region, but since actually this is called a polar coordinate, right? And also I have the partition like this orange, right? If I just draw, for example, let's say from here, from this point to this point, for example, let's say our r, or to any point, right? So r is also changing. Let me draw some rays starting, actually it's just starting from this O, 0, right? Some rays, that's the first one. Let's say this is the first ray, and the second ray, a third ray, a fourth ray, blah, 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 maybe M rays. And after that also the R, for example, the circles, right? This is how we partition this region. Why? Because here we have two things here. We have R and theta, right? I cannot just actually draw x-axis. If I say x-axis, what is x? We don't have such thing here. We have only two things that we know. That is r and that is theta. Anyway, if I just divide this into this form, at that time now we will have, let's say, n polar rectangles, right? It's a kind of, how we call this? It is it kind of wedge or something? Anyway, the kind of patch, let's say the small patch here that's covering this region. Okay, if you just pick one thing, all right, then after that we will here again, what is the definition? Here the definition is we need to pick one point from this region, right? And after that multiply the value of the function at this point by the area. Okay, so now we'll talk about this area. This area is important. How do we actually calculate this area? And we know that's in rectangle coordinate if, because our area is rectangle and just length times width, it gives us the area. So if it is the small one, this one is L is dx, W is dy. So this one is delta A. From here, what is delta A? Delta A is equal to dx times dy. Okay. So how about here? Here we have something like this. Here we have something like this. Right? Okay, let me just draw like this. And okay, so we are talking about this region. Okay, so we know that if this difference is, let's say it is delta r, okay, and this one is okay, let's say this one is if it is r, not r, okay, this small one is r and the long one is capital R, right? For example, here, how do you find the shaded region? We know that if you're given a sector, right, and the radius is r and this one is r, what is the area of the sector? The area of the sector is equal to 1 over 2 times theta. This angle is theta, and here we have r squared, right? And how about here? This shaded region here will be equal to 1 over 2 times, if this angle is theta, so that is theta times capital R squared minus, now I need to subtract this unshaded part, right? So here we have 1 over 2 times theta times R squared. Now from here, if you just simplify this, what do we get here? 1 over 2 times theta, capital R squared minus small r squared, that's equal to r minus lowercase r and capital R plus just r. This is r. Okay, that's equal to this. So now another one is, I need a bit more space. Okay. Why didn't I know this? Okay. So now we are talking about the shaded region, right? The shaded region, here we have, let me just write once again, our shaded region equals 1 over 2 times theta, and here we have r plus r, and here we have r minus r, right? And again, if you're talking about this, that is only the point. The rest is just similar, you know, what is those things. Here we are talking about the shaded region. Okay, how about if I just pick my point here? Let's say this point is, it is r sub k. Okay, at the time this r, this region will be, what is it? Since this one is, let's say delta r k. Okay, delta r k, or just delta r. From here, so what is this? This rk will be equal to r plus delta rk, right? Delta rk over 2, sorry, because this one is half. And how about this one, the big one? The big one will be, actually that is our not this one, rk, r plus this one. And how about we are talking about this capital R, we are talking about this lowercase r. Okay. So lowercase r is equal to, what is it? Here from here, r sub k minus delta rk over 2. Because that one is, this one is, we're talking about this one, that's delta rk. So that is 1 over 2 times delta rk. And how about capital R? That's equal to RK plus 1 over 2 times delta RK. Now, as you see here, from here, if I just add them together, what is R plus R? It will be equal to 2 times RK. How about if we subtract them, R minus R, these two things cancel each other, that's equal to just delta RK, okay? So now if I substitute into this equation, now we will have here 1 over 2 times theta, and R plus R, that's equal to 2 times delta RK. And how about R minus R? That's just equal to delta RK, which is equal to these two to cancel each other. And here we have
I think it's 2RK, sir.
hmm?
After that, it's 2RK.
2RK, right? It's 2RK. Yes, R plus R is 2RK. So here we have then theta times R sub K times delta RK. Okay, so that is actually one area, right? It's just one area. Also, this theta is small here. Let me just move back here. Now, how many such areas do we have? We have n area. Let's say here we have A1, A2, A3, right? And also, actually, I'm just dividing this theta into smaller angles. So that just one here, this small one, if I just name them, then A sub K, one area, will be approximately equal to delta theta K times R K times delta RK. Or let me just write this order, R sub K times delta RK times delta theta K. Okay, that is just, we're talking about this one area. And how many such areas do we have? N. All right, and we are just multiplying this by we are just forming our sum here. The sum is, because we are here, what is that? That K is equal to 1 to N. Um, Here we have that area, right? That's A sub K. Here we are multiplying the value of the function. Here we have R sub K and theta K. And here we have that's delta A sub K, which is equal to sigma here. K is equal to 1 to N F R sub K theta K. And what is this? That is R sub K and delta RK and delta theta K. Okay. Again, guys, here the main idea is see if you're given the region, we're just partitioning this into n some kind of paths or polar rectangles, let's say. And after that, we are just approximating one area. And if you just pick any point from that region and calculate the value of the function, right? And for example, again, what is the geometric interpretation of this? If our function is positive there, again, it just gives us the volume of the solid that is sitting on this region. We are just summing up all of these areas, right? And after that, when n goes to infinity, that gives us the double integral, because this sum always approaches, of course, if it approaches a single value, then that is defined as the double integral. That is what we are talking about, that S sub n, that is our partial sum, right? K equals 1 to n, that's our function in terms of r and theta, that is our area. And what is that area in polar coordinate? As we have just calculated here, it is just r times dr times dt. So that is representing our dx dy. And here our function here, and theta is changing from alpha to beta, right? It's just sweeping the whole region. That's theta is changing from alpha to beta, and also r is changing from g1r of theta to g2 of theta. That is how we obtain double integral and also evaluate the double integral using this formula. Okay, all right. Here, just let's have a look how we are going to do this. That's also exactly the same with the double integral in Cartesian plane. The procedure for finding limits of integration in rectangular coordinates also works for polar coordinates. If you remember, first we actually rectangular coordinate system, right? Where the axis changing first. And after that, we draw a line that is parallel to the y-axis, right? And we have to find where the line is entering the region and where it is exiting the region. So we have to mark, right? And after that, evaluate our integral. So number one, sketch the region and label the bounding curves. Guys, about sketching, some of the curves or regions are easy to draw, or if it is very complicated, so at this moment, immediately you can just use a lot of softwares. Like I usually use Graphmatic, for example. The size is very slow. Just draw this and see, okay? And I'll show you soon how to use this. Sketch the region and label the bounding curves. If it is easy, you can just draw with your hand. If it's a bit difficult, you can still try and also make sure that it's correct. Use some software and check this. And find the R limits of integration. And imagine a ray L from the origin cutting through R, the direction of increasing R. So mark the R values where L enters and leaves R. That's the same thing. And these are the R limits of integration. They usually depend on the angle theta that L makes with the positive x-axis. And find the theta limits of integration and find the smallest and largest theta values that bound R. These are the theta limits of integration. And let's take one example here. Consider the region which is bounded by the y-axis, x squared plus y squared is equal to 4. And the line y equals square root of 2. Okay, first we have to draw our axis and y-axis, and here we know that x squared plus y squared is equal to 4. It is the equation of a circle, right? It is the equation of a circle. In polar coordinate, we know that r squared here is equal to x squared plus y squared. That's equal to 4. So that's our r is equal to 2, right? So how about y is equal to square root of 2? So here one is a bit, let me just write here. This one is 1 and this one is 2. This one is 2. Right? I can just draw the circle here, but all right. So that is y equals square root of 2 is we're talking about this line, and our circle is something like this. It just continues like this. Right? So the equation of this circle, that is r is equal to 2, or since it's xy, just write here x squared plus y squared is equal to 4. So how about the equation of this line? That is y is equal to square root of 2, right? And how do we change this region into polar coordinates, right? How do they present this? So this one is square root of 2. Now from here, if you just find this, right, y equals square root of 2, what is the intersection point? Because they intersect here and here and here. We have 3 different points, right? So as you see here, if I just draw a line, let's say R, right? Or the angle, for example, our theta. What is the theta? First, I have to find this theta. Let's say it is alpha. And this angle is, it is just 90 degrees. And to do this one, let me just find the coordinates of this point. Then I can determine this alpha. So from here, square root of 2, right? If you just substitute here into this equation, intersection point, y is square root of 2, so x squared plus, what is y? It is square root of 2, square root of 2 squared is equal to 4. So what is x from here? It is 4 minus 2 is equal to 2. Is that right? It is 2. 4 minus 2 is equal to 2. So that is square root of 2. And we know that it's in the first quadrant. That's why it is positive. So here, that one is square root of 2 and the square root of 2. Right. So that means that what is our alpha then? Our alpha is pi over 4. So now I know that actually the theta is changing from pi over 4 to pi over 2, right? And how about our r? R is, for example, if I just draw any line, marker from here, any ray that passes through the region, as you see here, it enters here, right? And it exits here, right? Good. The entering point, right? That's y equals square root of 2. What is y? Y equals square root of 2. And we know that y is equal to r times sine of that's theta. That is sine of theta, right? So what is r from here? That r is equal to square root of 2. So what is r here? That r is equal to square root of 2 over sine of theta. Because also when theta changes, also r changes, right? That's equal to square root of 2 times cosecant of theta. And how about exiting part? It is here, right? As here, the r is constant. It's not changing. Everywhere is equal to 2. So here, this is, let's say R1, and this one is R2, that's equal to 2. That means that R is changing, then this R is changing from square root of 2 cosecant of theta to 2. Right? So now we can write our double integral here. So this double integral, theta is changing from pi over 4 to pi over 2. And how about our r? R is changing from square root of 2 cosecant of theta to 2. Now here our function, whatever it is, r and theta. And here we have r dr d theta. That is how we actually determine the integration limits. Okay, guys, any question? One are you there?
Yes, sir.
Where are you now, One Are you in Phnom Penh?
No, sir. I'm at my hometown,
Where is your hometown?
Bong Khmum province.
What?
Bong Khmum province, sir. Bong
Kabong
Khmum.
Kabong.
Yeah.
Kabong Kabong province. Dear Kampong Cham, I see. Okay, very good. So how is the internet connection there? Are you using Wi-Fi or 4G?
Just 4G, sir.
4G. I think 4G is much better.
Yeah, but
I don't know, at home also I have Wi-Fi. Sometimes when I connect this, it's not so stable. I don't know, maybe too many people use in our house. I have 4 kids and my one wife. So I just use 4G. For Zoom, it does not consume much, right? If I teach 1 hour, maybe like 300 megabytes or 400 megabytes, it's not so big. Okay. Anyway, guys, comparing to, I don't know, 2010, 2015, now it is much, much better, right? Internet connection is much better. And also it is much cheaper. So we have to just use it. And just for $2 in cell card, for example, I use cell card. How much do you give? Do you get? I use Big Love. So that is almost 10 gigabytes or 20 gigabytes, something like that. So that is more than enough. If you're just using, I mean, having classes and maybe not more than enough, but at least it is quite enough. Okay, let's continue then. Let's see another example. Find the limit of integration for integrating f over the region r that lies inside the cardioid, r equals 1 plus cosine of theta, and outside the circle, r equals 1. Okay, guys, while plotting some points, we can draw this. The cardioid means, as you see, cardioid, it means, I think, heart. It is in heart shape. That's why it is called cardioid. Okay, to do this one, for example, how do I draw this? If it is not so simple, I suggest you to use Graphmaticum. Let me just share my screen. Okay, now I think you have my screen, right? One name.
yes, sir. I can see.
Okay, I just opened Graphmatic as you see here. Okay, you can just download. It's like 2 megabytes or 3 megabytes, something like this. So our cardioid is r equals 1 plus cosine of t, right? It is cosine of t. That is our picture. And how about the second one? The second one is, it is just circle. R equals, is it 1 or 2? It is r equals 1. Okay, so the second one is r equals 1. That's our second graph. Draw this. And after that, I can just see this from here. For example, that is our shape, as you see here. If I get, I mean, this is how about drawing, okay? I just suggested to use Graphmatica. And after that, if you want to see where is the shaded part, you can just copy and paste into Paint and shade it inside the region, and you can see this, okay? So here we have, let me just open Paint, and here we are talking about this picture, okay? And all right. So that's our picture. Now, if I just shade this, we are talking about this region, right? We're talking about this region. Okay. That's we are talking about this region. And that's what we are talking about here. Okay. So find the limit of integration. As you see here, it says over the region R that lies inside the cardioid. If you just see the hard side, it must be lying inside the cardioid and outside the circle. And outside the circle, this is our circle in pink, right? So outside the circle is, we are talking about this region. So we are talking about this region. Okay. So now, as you see here, our theta. First, let's just determine the limits of theta. It just starts from here, right? Because our region is start from here. So that is our origin starting from here. We are talking about this ray, right? And until here, right? Until here. So that means that what is this angle? This angle is respect to x-axis. That is negative pi over 2, right? How about this one? This one is pi over 2. This angle is minus pi over 2. So that means that our theta is changing from minus pi over 2 to pi over 2. Now, how about r? Now, to find the r, let me just draw one ray starting from the origin, right? One ray. As you see here, it enters the region at this point and exits the region at this point, right? And what is the entry point of our r? It is constant. Everywhere it's just on the circle, right? So here we have r is changing from r to, how about exiting point? Exiting point is, here we have 1 plus cosine of theta. Then our double integral, let's say this I will be equal to integral theta is changing from minus pi over 2 to pi over 2. And how about r? It is changing from 1 to 1 plus cosine of theta. So here we have f of r theta and r dr d theta. Okay, here the question, just find the limit of integration or limits of integration. That's it. And if you know the function, now we can evaluate and integrate the function over this region. All right. So guys, let's just read this, and after that we'll have break. Okay. So if f of r theta is the constant function whose value is 1, then the integral of f over r is the area of r. It is exactly the same thing that we did, because if our function is 1, right, that means that the height of the solid is just 1, and numerical value of this integral, double integral, gives us just the area of that region. Okay. Guys, let's have some rest. Okay, 10-minute break. After 10 minutes, or what time is it now? It is 1:44. Maybe at 2 o'clock we will continue. Okay, so let's have some break now.